Hello friends, this is a concept video on the magnetic fields due to electric current. Okay. Now the questions of the type where they ask, given a wire which has a certain current, now you need to sometimes find the magnetic field at some point here, or otherwise given a current, okay, given a wire with a current, what is the force on certain charge with a velocity out here? Like if a charge q is moving with a velocity v, what is the force on this due to the current here? Such kind of questions are very common. Okay, such kind of questions where you need to find the magnetic field due to a steady electric current are very common in entrance exams. So that is what we'll do here. We'll find the tools, we'll get the tools to find the magnetic fields due to electric current. And the most important tool for that purpose is the Biot-Savart Law. Biot-Savart Law. Now, what does this law tell us is that if you have got a moving current, a steady current here, by steady current, I mean a current that is constant in time. I mean, if 5 amperes is flowing through the wire right now in a certain direction, it will flow in that direction for the entire time we observe it, and it will be the same constant value, that is 5 amperes. Okay, let's say this is the wire and the current is flowing through the wire. We need to find the magnetic field at a certain point P. Okay, now the current is flowing throughout the wire. That means at every little piece of wire. Okay, so there is a certain contribution towards the magnetic field due to this part, and then this part, and then this part, and then this part, and so on. Okay, every little part, we call those little parts dl, a small length. Okay, now every little part has a contribution towards the magnetic field created at P. Now let's say I is the current flowing here, and we'll just take this vector to be our R. Okay, the distance between the place where we want to find the magnetic field and the source, that is where the current flows. Okay, this is R, and the R will change as we change our dl. Like as we go a little higher, R will be from here to here, higher, then R will be from here to here, and so on. So this will be our R. That is the displacement. So now the magnetic field B at P, according to Biot-Savart's law, will be equals to integration with respect to dl, okay, and then I cross R. This R is not the same as this. This only has the direction and it has unit magnitude. That means the magnitude of this is 1, and we will divide this by R square. And this R is actually this R because we do this. Okay, R square. Now this R square will simply be R dot R, which is basically R square. So what you can do is you can simply take the magnitude of this and square this, or you can do the dot product of the vector. The same thing will come out, and in the front we'll have mu naught by 4 pi. Okay, let's understand this formula closely. First off, my magnetic field is a vector quantity and the direction is given by I cross R. Now whenever we have a cross product, okay, whenever we have a cross product giving directions, then what we can know is that we have I cross R, right? So I is in this direction here and R is in this direction. I cross R, let's make an arrow from I to R. Now curl your fingers just as the arrow points. So now I'll curl my fingers from I to R of my right hand, and then my thumb will point outside of the screen. If my fingers follow that arrow that I drew from I to R, then my thumb will point outward from the screen. And that outward is the direction of the magnetic field. The magnetic field at this point points out from the screen. So this is pointing out from the screen. So that is the direction of the magnetic field. You might even see in some books that dl is written in place of I here, because they are essentially the same vectors. Let me write it down. Mu naught divided by 4 pi integration. This integration is taken over the entire segment which contributes to the magnetic field. In this case, from here to here. Okay. Integration I cross R by R square dl. We have this. But what we can write is that since the magnitude of I is constant because it's a steady current, we can actually take I outside. Okay. And this dl is already a vector, like it has a certain direction. This it has this direction here and this direction here. So dl has got certain directions, right? So what we can do is take that direction for dl and then put it right here. Okay, so we get mu naught I by 4 pi dl cross r by r square without changing any physically significant thing right here. Now, let's see what this mu naught by 4 pi is. Everything else is clear, so let's see what mu naught by 4 pi is. Well, mu naught equals to 4 pi times 10 to the power 7 Newton per ampere square. Okay. Then what will be the unit of the magnetic field? The unit of the magnetic field will be given by first the unit of mu pi, that is unit. Okay. So I'll do Newton per ampere square, and there's an ampere due to that current, and then there's dl which is in meters and r square which is in meter square. So these things cancel off. This cancels out with this. So I get the unit to be newtons per ampere meter. Okay, and this unit is called the Tesla. Now that is the magnetic field due to an electric current. That is your Biot-Savart Law. If you want to see some questions where Biot-Savart Law is used, then do check the links in the description below. Now, the next tool that we can use to find out the magnetic field due to an electric current is the Ampere's law. Ampere's law. Now, what Ampere's law says is that if you have some current, okay, in some wire going this way, then what you do is you draw an Amperian loop around it, and if you integrate over the loop, if you integrate the electric field, okay, if you integrate the magnetic field, if you integrate the magnetic field over the loop, then what you get is mu naught times I inclusive. Well, you may wonder, how will I integrate the magnetic field if I actually need the magnetic field itself, right? So for that, what we do is we usually take cases where it is symmetric. Okay, where we can take the B out of this and we usually only integrate dl, and that will give us B. Okay, we usually have this as in the case of a straight conductor, okay, which is infinitely long. What we have is, let's say this is a straight conductor which is infinitely long. Then the direction of our magnetic field will be in the circle itself. Like, since your current is going this way, then use Biot-Savart's law and think, now this is the radius, okay, from here to here. Now your magnetic field will be given by your right hand thumb rule. Okay, how you do that is, here's the current I, here's your radius, so draw an arrow from the current to the to this point where you have the radius of the circle. Here is the point where you want to find the field, and if you curl your finger, it will come straight. If you curl your finger, it comes straight out of the screen, and that is this circle. Okay, here it goes inside the screen. This is the direction of your magnetic field at any point on the wire, on the loop, and dl has the same direction. So two vectors that are in the same direction, you are taking their dot product, which means this will simply be b dl. because the dot product will be BDL, because cos of 0 will give you 1, mu naught I inclusive, and then you have got B equals to mu naught I inclusive divided by integrate dl. If you integrate dl over the circle, okay, then what you get is simply the circumference, that is 2 pi r. Okay, and that is the magnetic field due to an electric current at any point. If you want till here, then you will extend r till here. So that is the electric field due to an infinitely long straight electric wire. See, Ampere's law is much easier to use, okay, but it is not applicable everywhere. In fact, Ampere's law can only be used for infinitely long straight wires, okay, or an infinitely large sheet where a surface current flows, or a solenoid that is infinitely long again, or a toroid, which is basically a solenoid but circular. And that is why Ampere's law's applicability is not as good as Biot-Savart's law. But simply knowing this much, that the magnetic field around here, okay, if you integrate it, you get mu naught I enclosed. That will help a lot with many questions. If need be, we'll do the other cases later on, but you can try to apply it yourself to different symmetries. Thank you for watching the videos, and if you have any doubts, comments, suggestions, feedbacks, anything at all, please let me know in the comment below.